Assalamu alaikum, dear students. Today our topic is osmotic pressure, a fourth colligative property. We will derive the expression, we will explain osmotic pressure and derive the expression for the osmotic pressure. We will also determine the molar mass of the non-volatile solute by this osmotic pressure. Now, before discussing osmotic pressure, we must know what is osmosis, and osmosis डिस्कस करने से पहले हम we must know what is a semi-permeable membrane. So, semi-permeable membrane. It is a membrane which allows only solvent molecules to pass through it, but not bigger molecules like solute particles. The examples are the parchment paper, the animal bladder, that is the pig bladder, goat bladder, and cellophane. So we will first define semi-permeable membrane. We will write its definition. It is a membrane which allows solvent molecules to pass through it, but not bigger molecules like solute particles, e.g. parchment paper, cellophane, pig bladder, or goat bladder. We can also use copper ferrocyanide as semi-permeable membrane. These membrane, they appear, these membrane appear like continuous sheets or films, have submicroscopic pores और holes. तो इनको सब माइक्रोस्कोपिक पोर्स होते हैं और होल्स होते हैं through which the solvent passes. Now this is the definition of semi-permeable membrane. Now what is osmosis? तो osmosis explain करने के लिए we will demonstrate an experiment. We will take a beaker. We will take a beaker and we will divide it into two compartments by semi-permeable membrane. In the one, we take the solution of copper sulfate, and in another compartment, we take the solvent, which is the water. Now, due to the osmosis, the water molecules pass into the solution, due to which, as a result, the level of the solution in one compartment rises and the level in the solvent part decreases. Again, also we can explain this osmosis if we take concentrated solution of copper sulfate in one compartment, and in another compartment we take dilute copper sulfate solution. So, due to the osmosis, since the two solutions are separated by a semi-permeable membrane, due to the osmosis, the solvent molecules from the dilute solution pass into the more concentrated solution, due to which the level of the solution rises and that concentrated solution rises and that of the dilute solution falls. Now we can define osmosis. It is the process of passage of solvent molecules from solvent into solution, or from less concentrated solution to more concentrated solution through semi-permeable membrane. So the osmosis is the process which involves the passage of the solvent molecules from the solvent into solution, or from less concentrated solution to more concentrated solution through semi-permeable membrane. तो अगर हम instead of taking the solution and the solvent, again we will take beaker. In this beaker we take concentrated solution, and here dilute solution. The solvent from the dilute enters into the concentrated solution, and its level rises and its level falls. So this is also due to the osmosis. Now we can demonstrate this osmosis in the laboratory or at home by taking two eggs of similar size. ये osmosis explain करने के लिए a simple experiment हम करेंगे. We will take two eggs of the similar size. We put these eggs in the dilute solution of hydrochloric acid for some time. The hard shell of eggs contain calcium carbonate, which gets dissolved in the hydrochloric acid. Therefore, the soft semi-permeable membrane of the egg remains intact. इसका मतलब ये है कि इसका जो आउटर शेल है वो डिजॉल्व हो जाएगी हाइड्रोक्लोरिक एसिड में, और जो इनर पोर्शन है एग का उसमें दैट विल रिमेन इंटैक्ट. सो we take one egg in a solution, in a brine solution. एक egg को जो हमने जिसको हमने shell remove किया, we put one in a brine solution. Brine is a sodium chloride solution, and another we put in a beaker containing water. This brine is sodium chloride dissolved in the water, so this is sodium chloride solution, and we have the another egg dissolved in the solvent, which is water. Now the egg which is put in the water swells, and the egg which is put in the brine, it shrinks. Now why this swelling? The swelling takes place, the water molecules enter into the egg which contain concentrated fluid through the egg walls which act as semi-permeable membrane. So due to the osmosis, water enters the egg in the first case, in the first beaker in which we have taken the water. In the second case, where the shrinking has taken place, the water in the fluid, present in the fluid, comes out of it and passes into the salt, which is more concentrated. So here the osmosis takes place from egg, the solvent molecules pass from less concentrated egg fluid into the more concentrated salt sodium chloride, and in the earlier case the water molecules enter from solvent into the egg which is concentrated solution. So in this way we can explain osmosis. Now we will take osmotic pressure. How we can explain osmotic pressure? We will take a thistle funnel. This is a thistle funnel, and we will tie a semi-permeable membrane like cellophane. Its mouth is tied with a cellophane semi-permeable membrane, that is cellophane. Or we can tie pig bladder. Now this is, if we invert it, this is inverted thistle funnel, and which contains, the mouth of which contains semi-permeable membrane. And in this inverted thistle funnel we put sugar solution. हम इसमें sugar solution डालेंगे. So we take inverted thistle funnel, we take sugar solution in this inverted thistle funnel, and we put this thistle funnel in a beaker containing the solvent which is water, because the sugar solution is a solution which is prepared by dissolving sugar in water. So in sugar solution, water is the solvent. So we put it in the water. Now what happens? Due to the osmosis, the water molecules enter into the solution through the semi-permeable membrane. As a result, the level of the solution in the thistle funnel rises. Now, the additional hydrostatic pressure. What do you mean by additional hydrostatic pressure? The pressure exerted by the solution is exerted on the solution. And ultimately, a stage reaches when the level of the solution in the thistle funnel remains constant. That means the entry of the solvent molecules, the entry of the water molecules in the thistle funnel has stopped. At this stage, the hydrostatic pressure is just sufficient to prevent the further entry of the solvent molecules into the solution. This equilibrium hydrostatic pressure on the solution required to prevent the entry of solvent molecules into solution is called osmotic pressure. So osmotic pressure, this is the initial stage, this is the final stage when the solvent has entered into the solution through the semi-permeable membrane. Now what has happened here, ये जो सॉल्वेंट वाटर मॉलिक्यूल्स इसमें हो गए तो सोल्यूशन की लेवल जो है वो बढ़ गई और सोल्यूशन यहाँ तक आ गई और यहाँ से ये स्टॉप हो गई, कांस्टेंट रह गई. At this stage the pressure exerted by the solution, that is the hydrostatic pressure, is sufficient to prevent the entry of the water molecules in this solution. This equilibrium hydrostatic pressure is called the osmotic pressure. Now, alternately, we can explain it in another way. We will apply the pressure and we will stop the entry of the solvent molecules into the solution, or we will stop the osmosis by applying the pressure. Now, for this, we will take a vessel. It is a vessel, and we divide it into two compartments. One compartment is fitted with this is a narrow tube, and this compartment contains solvent. The another compartment is provided with a wider tube which is fitted with a piston, and this compartment contains solution. Now what happens? Due to the osmosis, the solvent molecules tend to pass into the solution. So what happens in the solution? इस solution piston तक है, but this is frictionless piston. What happened to this? When the solvent molecules, as a result, the piston will tend to move outside. It will move outside, and the level of the solvent in this component will fall. That will be seen through this narrow tube. Now, what we will do, if a pressure is applied on the piston, we will apply pressure on the piston so that the entry of the solvent in the solution is prevented. How we can observe that? By applying the pressure, we will see that the level of the solvent in the solution, if it remains as it was in the earlier case, if it remains the constant, that means we have stopped the movement of the solvent in the solution. Thus, the external pressure or the desired pressure applied on the piston or applied on the solution to prevent the flow of the solvent into the solution is also known as osmotic pressure. So यहाँ से हम osmosis stop करने के लिए pressure apply करते हैं. वो कैसे हम measure करेंगे? By seeing the level of the solvent in the solution, that the level remains constant. The pressure measured, the pressure applied is called the osmotic pressure. Clear? And now we will take the expression for the osmotic pressure. Expression for osmotic pressure. Van 't Hoff scientists studied the osmotic pressure of a large number of the dilute or ideal solutions, and he concluded that these solutions, these dilute solutions or ideal solutions, these behave like ideal gases. and different gas laws are applied to these solutions as well. So what he observed that these dilute solutions or ideal solutions, these behave like ideal gases and different gas laws are applied to these solutions, and hence it was observed that it was observed that the osmotic pressure of a solution is directly proportional to molar concentration of the solution and its temperature. So mathematically we can write osmotic pressure, which is denoted by pi, is proportional to C, which is the molar concentration, and it is directly proportional to the temperature. So we can write pi osmotic pressure is proportional to Ct, or pi is equal to RCT, where R is constant called solution constant, and its value has been found to be equal to gas constant. So we can say this R is just like the gas constant. Now pi is equal to C or Ct, but C is the molar concentration. It is equal to N, the number of moles, by V, where N is number of moles of solute, V volume of solution in liter. Substituting this value in equation first, we get pi is equal to R N by V into T, or pi V is equal to N R T. This is the equation for the osmotic pressure. It is also called Watt. This equation is also called Van't Hoff's equation. Van't Hoff equation. Now we have derived the equation for the osmotic pressure. Now we will determine the molar mass of the non-volatile solute. So derivation of the expression for the molar mass of the solute. Now, determination of molar mass of solute by osmotic pressure. Now we have the equation for the osmotic pressure, which is pi V is equal to N or T. N is the number of moles. If WB grams is the mass of solute having molar mass MB. So B we write for the solute, WB is the mass of the solute in grams, and MB is the molar mass of the solute. Then N is equal to the mass of the solute divided by its molar mass. Again we will substitute N in equation second. We will get pi V is equal to N की जगह WB by MB into RT. So this is WB by MB into RT is equal to pi V. Now we have to calculate the molar mass of the non-volatile solute. So MB will be equal to WB RT divided by pi V. This is the equation for determining the molar mass of non-volatile solute. Thus knowing all the values for WB, mass of the solute, or gas constant, T, temperature, pi, osmotic pressure, and V, volume of solution, the value of MB, molar mass of the solute, can be determined. So we have derived the expression for the molar mass by this osmotic pressure, from this osmotic pressure. Now we will solve a numerical based on this equation, how we can determine the molar mass of the solute. Now a simple numerical. Numerical is 200 centimeter cube of an aqueous solution of the protein contains 1.26 grams of the protein. The osmotic pressure of such solution at 300 Kelvin is 2.57 into 10 raised power minus 3 bar. Calculate the molar mass of the protein. We have the aqueous solution of the protein, that means we have dissolved protein in the water and we have taken the protein as 1.26 grams. The whole solution becomes equal to 200 centimeter cube. This is the volume of the solution, and we have taken the temperature of the solution 300 Kelvin, and the osmotic pressure of this solution is 2.57 into 10 raised power minus 3 bar. Now the volume of the solution is 200 centimeter cube, we will convert it into liters. 1000 centimeter cube is equal to 1 liter. So 1 liter, so we will divide it by 1000 in order to convert it into liter. So it will become 0.2 liter. Again we have the osmotic pressure in the bar, and here we will convert this or the gas constant into bar. We know 10 square joule is equal to, or 1 liter bar is equal to 10 square joule, or 1 liter bar is equal to 100 joule. So in order to convert into liter bar, 100 joule is equal to 1 liter bar, we have to divide this by 100. So when we divide it by 100, its value will be equal to 0.08314 liter bar per Kelvin per mole. Instead of joule, we write liter bar. Now, here we will take only after the 3 place of the decimal, that is 0.083, and the unit liter bar per Kelvin per mole. And we will take the equation, that is pi V is equal to, molar mass of the non-volatile solute is equal to, that is RT WB divided by pi V. Substitute the values. WB is equal to 1.26 grams into R is 0.083 liter bar per Kelvin per mole, into T is 300 Kelvin, divided by pi is 2.57 into 10 raised power minus 3 bar, into V, that is 0.2 liter. Now first we will see the unit. This is liter, liter cancel, bar, bar cancel, per Kelvin, per Kelvin cancel, per Kelvin and Kelvin cancel. So we have gram per mole. Now 1.26 we will write 126 divided by 1000. Similarly we have decimal in the denominator, 2 digits on the right side of the decimal, so it will become 126 whole divided by 257, because this is also divided by 100 and this is also divided by 100. 100 cancel. Again we have 83 divided by 1000, 0 0 0 and 1. 1000 means 10 ka cube into 10 raised power minus 3 already, into 300 gram per mole, divide by, this is 0.2, we will write 2 whole divided by 10, 10 हम ऊपर ले लेंगे into 10. So this will cancel, ये decimal भी cancel हुआ. Now 126 divided by 257 into 83 into 3000, ये 10 divide by 2. Then we will solve it. Its value comes equal to 62,038 grams per mole. This is the value of for the molar mass of the non-volatile solute which is the protein. The molar mass of the protein is 62,038 grams per mole.